Okay, beginning with example 3 here, we have a particular bacterium that takes 10 minutes to double. So 10 minutes is how long it's going to take one bacteria to then turn into 2, and then 10 minutes after that, that 2 would turn into 4, so at the 20-minute mark we would have 4. 10 minutes after that, that 4 would turn into 8, and so on from there. So doubling time means our base would be a 2. We've got 100% plus 100%. So when I go to write my equation for this, I know my base has to be a 2. The initial number of bacteria was 50 here. So that's my A value for my exponential function. I'm going to use the capital letter P for population. My exponent, I want to see how many groups of 10 minutes I actually have. So if my time was 30 minutes, my t would be 30. 30 divided by 10 would give me a 3. It's actually doubling 3 times here. So that's why my exponent looks the way it does. Now we need to make sure we define our variables here, so I'll quickly do that. Now notice when I put my let statement here, I've got P representing the population or the number of bacteria. My T represents the time, and I have my units here as well as being in minutes. So make sure that when you are defining your variables on your test that you are stating units that go with that. That's a part of your communication mark, things that I look for when I'm marking that. Now, in terms of solving this question, we want to know how long, so it's T we're trying to solve for, it will take for the culture to have over 1 million bacteria. So I'm going to let my population be 1,000,000. So where I have the P, I'm going to put 1,000,000, which is a 1 with 6 zeros. And that population has to grow, or is growing to 1,000,000 from the 50 that we started with. All right, now I want to solve for that exponent. To be able to do that, I'm going to start getting t by itself, but the first thing I'm going to undo is the times by 50 by dividing both sides of the equation by 50. 1,000,000 divided by 50 is 20,000, and that's going to equal my 2 to the exponent t over 10. Now, to get that t out of the exponent, to be able to actually solve that, we're going to take the common log of both sides. So I'm going to do the log of the 20,000, and I'm going to take the log of the 2 to the exponent t over 10. Having trouble writing and talking at the same time. There we are. Okay, t over 10. Come on, 10, get written there. All right, now I'm going to use that log rule that says that exponent, t over 10, moves down in front. That's one of our log laws. So we're still going to have the log of 20,000 on the left hand of the side of the equal sign, and that's going to equal t over 10 times the log of 2. And then we're going to start getting t by itself here. I'm dividing the t by 10. Let's multiply both sides by 10 to undo that divide by 10. But again, we got to multiply the other side by that. So now I've got 10 times the log of 20,000, and that's going to equal t times the log of 2. So t is being multiplied by the log of 2. To undo that, I'm going to divide both sides of the equation by the log of 2. There we go. So now that undoes that and leaves us with t. So we can put all that calculation here into our calculator to get what t is equal to. Okay, so pop that into your calculator, get an answer. The answer I got, and hopefully I haven't made a mistake, you should double check my work always, because, you know, I do make mistakes from time to time, because I'm only human. And I get 142.88 minutes. Okay? Now, we wouldn't normally say, well, it takes 142.88 minutes. We're going to say it takes, 2 hours and something here. So we're going to change that time into its hour form, or at least find out how many hours we would have out of that. We're going to see how many groups of 60 minutes will fit into that. Okay, so divide that by 60, and I have pre-done that on my calculator. And again, I hope I did not make any mistakes with that. I got about 2.38. So that's 2 full hours, so 2 hours, and then 0.38 of an hour, which I'm going to turn back into minutes. So 0.38 hours, it's that many of 60 minutes, that much of 60 minutes of an hour. and that part gave me about 23 minutes. I just went to the nearest minute there. Okay, so it takes about 2 hours and 23 minutes for that culture to grow to be 1 million bacteria. So make sure you include a concluding statement with that. Again, part of your communication mark comes from the final statement that you put with that problem. All right, moving on to the next question here. Radioactive iodine 131 has a half-life of 8 days. So that means it's going to cut its mass in half every 8 days. So we're starting with 40 milligrams, and then 8 days after it started with the 40 milligrams, it will be cut in half. So it will have 20 milligrams left. And then 8 days after that, it will now have 10 milligrams left because the 20 gets cut in half. And then 8 days after that, the 10 gets cut in half and we have 5 milligrams left. So our equation for this, we could have M for mass. The mass started with 40 milligrams, our initial value. We're reducing it by a half, by 50%. So the base is 1/2. 100% minus 50% is 50%, or 0.5, or 1/2. Now, the half-life is 8 days. We want to take the time that it's sitting around and see how many groups of 8 days will we actually have out of that. So T this time is defined to be in days, and M is our mass in milligrams here. So let's make sure we have our let statements there for that. So again, when I do my let statements, I have the mass, and I'm saying I'm using the units milligrams, and T is my time, and I'm saying the unit is days. So again, good let statements will have the units included in there. Now, how much will remain after 30 days? So we need to figure out our mass, and we've been given what the time actually is equal to there. Our time is 30, so we're going to pop 30 in where the T is, and then we're going to solve that just using our calculator. Just putting those numbers in and getting values out of that. So 30 divided by 8, which, by the way, I think is 3.75. All right, put that in your calculator. When I did that, I got about 2.973. So after 30 days, there's only just a little under 3 milligrams left there. So again, finish that with a therefore statement. So after 30 days, there will be 2.973 milligrams left. Part B is asking how long, so it's time that we want to figure out, how long will it take until only 1 milligram remains. So this is like example 3, where we're going to put the 1 milligram in for the actual mass, and then we want to be able to solve for the T. So why don't you put the video on pause, try it, and then you can see how you do on this. Okay, so I have now done my solution here for 4B. If you are uncertain about anything that's happened in my solution there, and you're not sure about what's going on, please make sure that you ask me for some extra help with that. In the end, I got that it took about 42.6 days, so about just over 42.5 days to reduce to 1 milligram. All right, hopefully that makes sense for you.